Okay, welcome back everyone to the final talk of the conference. So we'll have Dominic Ryder talking about the idealization paradox and Hawking radiation, and following the talk, Saakshi Dulani will be giving comments on the talk. So take it away, Dominic.
Now?
Yes.
Great. I should start by saying what an honor it is to speak at this conference with such amazing physicists and philosophers of physics. I'm very, very happy to be here. Also, I'm the last, so I hope there's enough energy left in the room to get through one last session. And seeing as I'm last, I should take the opportunity to thank the organisers for bringing this together, Chris, Francesca, and Nick.
May I clarify at this point? Nick did a lot of the program organizational things, and the two local organizers deserve the credit for all the local organization. I'm not really sure what my name does on the organizational credit, so it's mostly the other three.
Thank you for the clarification. Okay, let's get going. I'm going to be speaking about Hawking radiation and what I call the idealization paradox. Hopefully the relevance of the Wittgenstein quote will become more clear. I'm sure everyone knows what Hawking radiation is. It's very naively a thermal spectrum of radiation seen at future null infinity in black hole spacetimes. We believe in this primarily because of Hawking's original 1975 derivation, which was specified by Bob Wald later that year. And then I've included these two because these are sort of the increasing rigor heritage. As mathematicians identify parts of the derivation they're not particularly happy with, we get algebraic quantum field theory, which is the real, obviously you can't do anything with it, but at least it's mathematically consistent. There's a derivation of Hawking radiation there. And then Friedenhagen and Haag in 1990 gave what they called a watertight derivation. And to quote Miklos Rede, Miklos trusts Friedenhagen and Haag. And so if that one's not mathematically rigorous, nothing is. And I'm going to argue that all of these have an inconsistent argument style, which I think is somewhat controversial, but hopefully I can convince you. Let's set the context. People talk about Hawking radiation because of the black hole information paradox, normally. Here's Preskill saying that it's going to presage a revolution in fundamental physics. And Wallace saying that if we're lucky, we're going to learn something deep. So there's a lot of excitement seen by these two review articles, separated by about 30 years, which together have over 500 references. So people are talking about this, people are writing about Hawking radiation. It's also important for two other philosophically interesting topics, black hole thermodynamics and the transplanting problem, both of which have various degrees of, various levels of interest for future physics and current physics. This is a new paradox. This, I take, is a contribution to that literature, but disconnected from both of those two topics, and it stands independently. I claim that certain way idealizations are used in derivations of Hawking radiation leads to those derivations being inconsistent with evaporation. Now, I assume all of the stuff that's normally assumed. I assume that the black hole models we usually use are good models of black holes. I assume that the QFT uncurved spacetime framework is a good framework. I assume back reaction arguments are reasonable. And I get this paradox, and then I claim that it does require something new to resolve it. Maybe that's going to be quantum gravity. Maybe that's going to be some sort of encoding of local structure by global structure. There's other ideas we will talk about. So here's how it works. I want to derive Hawking radiation, so I write down the space-time. I use a certain space-time. Let's say a non-rotating, uncharged black hole formed by stellar collapse. I'll talk more about these diagrams in a bit. I model a quantum field theory on that space-time, and I derive a thermal spectrum of particles at future null infinity. But then I use back reaction arguments, and I infer that the black hole, in fact, is going to evaporate. But this is not an evaporating black hole. Once this black hole is formed, it exists forever. So I throw that away. I go, that's not real. That doesn't actually exist. And instead I have this. Again, I'll talk more about these diagrams in a bit. But now this black hole is an evaporation black hole. So what I'm doing really is I'm de-idealizing my derivation. I'm saying, this is what I think really physically represents black hole spacetimes. But now what I need to do is I need to consistency check. I need to go, does my derivation still work on this spacetime? Can I still derive this thermal spectrum of particles? And I'm going to claim that assumptions necessary for those 4 derivations I listed break down in this spacetime. So I've thrown away the spacetime I used to derive Hawking radiation, and yet I keep the conclusion that Hawking radiation exists. It's a very weird argument style. So here's it set out in premise form. 1, if spacetime exhibits some set of properties X, which I'll elucidate later on, then Hawking radiation exists. If Hawking radiation occurs, then black hole evaporation occurs. These are the standard back reaction arguments. And then this is what I'll defend in my talk, the inconsistency claim. If black hole evaporation occurs, then spacetime doesn't exhibit the set of properties X. And then you also need a spacetime postulate to get the original derivation off the ground. Now, premise 1 is basically a mathematical fact. It's what exists if you go and read Hawking's original paper or any of the other papers. Like, that's what's established in those papers, premise 1. Premise 2 is obviously a bit more contentious. We don't have a good theory of back reaction, but we have various well-established approximation regimes, and until the second to last slide, I'm not going to question that one. And then spacetime postulate, as I say, is what is needed to get premise 1 off the ground. So the other 3 premises are fairly robust. It's the third premise, which I want to talk a bit more about. I'm going to do some consciousness shaping now to try to make sure you're getting the right picture of what I'm saying. I don't think this is a reason to be skeptical of Hawking radiation. And the obvious reason is, I don't claim that the 4 derivations I listed exhaust all possible derivations of Hawking radiation. There's very plausibly evaporation-consistent derivations. And then my argument just doesn't work. But as I'll talk about a bit about later, even if those derivations are evaporation-consistent, the derivations I list aren't. So there's still a paradox for those derivations. So you can think of the idealization paradox more specify to derivations of Hawking radiation rather than attacking Hawking radiation simpliciter. It's not just another formulation of the information paradox, it's a different thing. And also it's not just a complaint about physical assumptions. For example, you might complain that we're using infinity to model the black holes, future null infinity, and it's really finite. I accept that those are good modeling assumptions. I accept that we can de-idealize in those ways. This is about a logical structure of an argument. What this talk is, it's a genuine paradox. It's a road to investigate how we're modeling with general relativity and QFT and curved spacetime, and it's an insight into the nature of Hawking radiation. Okay, here's the plan. I'm going to give a brief primer on black hole physics and QFT and curved spacetimes, but I might truck through that at some speed. And then sketch Hawking's original derivation and argue that it's evaporation inconsistent. I'll repeat it briefly for Friedenhagen and Haag and Haag's approach and the algebraic approach, and then I'll do the interesting bit and canvass possible resolutions and the lessons to be learned. So first, the primer. You're aware, we model black holes often with these conformal diagrams, and I'll put them up a bunch. The standard non-rotating uncharged spacetime is Schwarzschild, and this is maximally extended with this period, this region, section 2 being the black hole region. But we think physical black holes form through gravitational collapse. And so we model a star existing at time like past infinity and collapsing into forming a black hole. And so we throw away most of that space-time and are left with that, which I call collapsed Schwarzschild. And the exterior of the collapsing matter in collapsed Schwarzschild is isometric to the exterior region here. And that isometry is going to be used a lot in the derivations. The 2 properties of these spacetimes, which are really important, are stationarity and global hyperbolicity. Stationarity means the spacetime emits a time-like killing vector field, but what you should read with stationarity is time translation symmetry. The spacetime doesn't change as you move into the future. Global hyperbolicity, the technical definition is that it emits a Cauchy surface, but the intuitive thing is that it emits a deterministic, well-posed initial value problem because the Cauchy surface determines the entire spacetime. So we've got a spacetime, so now we need to define particles on that spacetime. So we define phi, some massless complex valued non-interacting scalar field which obeys the covariant wave equation. And then there's obviously a lot of technical work which you do to define a quantum field theory. The important part, just picked up in these derivations, is how we define particles in that process. We select the positive frequency solutions to the covariant wave equation as the physically real ones. And importantly, it's positive frequency with respect to some time translation symmetry. So you define a time-like killing vector field, and that allows you to define a particle. So particles are defined, and a particle interpretation is defined with respect to some time-like killing vector field. This is obviously very easy in Minkowski, we have one, and in our maximum extended Schwarzschild and the exterior of collapsed Schwarzschild, we have stationarity, and so we're going to have this. Time translation symmetry is not generic though. Any spacetime in which you have change, you're not going to have time translation symmetry. If you have gravitational waves, you don't have a time-like killing vector field. So using this definition of a particle interpretation, we get particle creation in Hawking style. So imagine I've got a spacetime composed of three regions, two stationary regions sandwiching a non-stationary region. Now on those two stationary regions, I have a particle interpretation. I don't have one in the non-stationary region. And so if I stipulate that there are no particles in this region, the two particle interpretations aren't going to map onto each other. And so you're going to have a different particle interpretation in the next stationary region. And so you're going to have a particle content, a non-zero particle content in that region. And that's particle creation. You get, there's technical ways to do this, but you have two stationary regions, two particle interpretations, no particles in the past, so with respect to the future, you have particles. And that's how the mainstream interpretation of the Hawking effect works. So we get the Hawking effect, and then you have the black hole evaporation. It's obviously maybe slightly more contentious in philosophical communities, but in physics communities, it's definitely the consensus. We don't have a good theory of back reaction, but you can make energy conservation arguments based on the ADM energy. And you have people saying things like, on pain of a drastic violation of energy conservation, you need black hole evaporation. And then, once you get down to a Planck scale black hole, as the black hole is losing energy, you have Hawking saying things like, it can't really do anything else except disappear. And so, this is the diagram that Hawking wrote down in his original paper, and you basically get to the Planck scale black hole, and then you throw it away, and you replace it with Minkowski. And this is what I call evaporation Schwarzschild. And so the purpose of all that is to understand how we get from collapsed Schwarzschild to a different spacetime, evaporation Schwarzschild. Oh, got loads of time. Okay, good. That's. Are there any questions about that? Did I go through anything too fast? Great. Now let's sketch Hawking's derivation. Yeah.
Are you making infer the you just leave? Did you say anything
Could
about?
you put your mic on?
Sorry.
I think by now I would have got it. Are you making any assumptions about the evaporation event point, or are you just kind of leaving that?
You'll actually see that I don't need to say anything specific about the evaporation event point. For pedagogical purposes, I use evaporation Schwarzschild as it's normally written down, which at the evaporation event point it's a naked singularity. So obviously we think that's going to be resolved somehow. But that's not going to be important, the argument. So we begin with collapsed Schwarzschild. And then we could cover it with Eddington-Finkelstein coordinates. You don't need to know much about these, but what I want to point out is it uses this constant mass term, m, which is the mass of the black hole, to define our ingoing and outgoing null coordinates. And then you define a particle, a mode, at future null infinity, that p omega on square plus. And then what we're going to do is we're going to propagate it back along the horizon through the collapsing matter region. Now, the collapsing matter region is that non-stationary region I talked about in the particle creation model. So we propagate it through the non-stationary collapsing region and back onto past null infinity. And then we decompose our late time modes into early time modes, and we decompose our creation and annihilator operators in the same way. And so I can define 0 minus here, the state is the state which has 0 particles with respect to the particle interpretation on past null infinity. And so I can write down the number operator, and it's the number operator according to the particle interpretation on future null infinity, on the state which has 0 particles with respect to past null infinity. And you get this term, which this is called a Pogulya-Bov coefficient, and that's going to tell you how many particles on future null infinity, according to the particle interpretation. So the whole game is determining those Pogulya-Bov coefficients. The way Hawking does it is he exploits an isometry with the exterior of maximally extended Schwarzschild. He thinks, okay, I'm propagating my mode back. How would it behave if I was propagating my mode along the path horizon? He connects null vector, which is normal to the horizon, to these planes of constant phase, which are these modes being propagated back. And imagines them being propagated back to the Bifurcated horizon, which is this bit here. And he thinks about how it behaved there, and he draws some inferences. Basically, you can write down an equation which relates the phase of these constant phase surfaces to this normal vector being propagated along the horizon. And then you find the form of the modes on the past horizon, and you extract the Pogulya-Bov coefficients, and you learn that there's a thermal spectrum of particles at future null infinity at the Hawking temperature, at t equals kappa over 2 pi, where kappa is the surface gravity of the black hole. So I went through that in very, obviously, heuristic terms. I didn't write down anything precise. But you can see the basic structures going into this derivation, hopefully. Our task now, as you may have inferred from this talk, is to determine whether this derivation can be carried out in evaporation Schwarzschild. So the first property, which is necessary for Hawking's derivation, which breaks down in evaporation Schwarzschild, is global hyperbolicity. This isn't globally hyperbolic. As I said in answer to Nick's question, there's a naked singularity at the evaporation event, and neither of these are Cauchy surfaces. And global hyperbolicity is necessary because we need the modes on past null infinity to determine the modes on future null infinity. And that determination is given by a spacetime which has global hyperbolicity. But this isn't a problem, because I can just take the maximal globally hyperbolic development of past null infinity and just use that and see, well, can I derive Hawking radiation in that, the mghd of square minus? And this is why I don't need to assume much about the evaporation event, because I'm just doing everything in the region before it, in some sense. So I can recover global hyperbolicity. That's not going to be the sort of property X which is going to worry us. But unfortunately, Hawking's derivation fails in the maximal globally hyperbolic development of square minus. So what are the differences? The exterior solution of the maximal globally hyperbolic development of square minus is no longer isometric to maximally extended Schwarzschild. But the black hole mass is changing. And so it's just not true that this is the same isometric to any region of that maximum extended Schwarzschild which I used before. The spacetime is also no longer stationary, obviously. The black hole's changing mass, right? If you were following any time world line through this, you'd see the mass of the black hole changing. This is going to be less relevant to Hawking's derivation, but it's going to be important for Friedenhagen and Hart. There's also no longer a global time function which goes to infinity. Global time function is finite, it gets to the Cauchy horizon and it stops. So it's only finite into the future. And so those differences mean that we can't use those Eddington-Finkelstein coordinates we wrote down. They use a constant mass term, and we don't have a constant mass black hole. And so we don't have a good account of how mode defined with respect to those coordinates are going to behave. I mean, you can write down maybe ingoing, outgoing, no coordinates, but the analysis of those modes depend upon using Eddington-Finkelstein coordinates. We can't use the equivalence of the exterior region with maximum extended Schwarzschild either. And so just intuitively, right, I'm propagating modes along the horizon, connecting them to the horizon, and seeing how those modes change as I propagate them back. If the horizon is now changing, then the behavior of the modes, what happens to those modes, is also going to change. And so, intuitively, we expect something different to happen based upon the way the derivation works. And so, Hawking's derivation just doesn't go through. Like, assumptions which are used in Hawking's derivation of the thermal spectrum break down. Oh, what have I done? Yeah. Now, I'm in a room of philosophers, so you're probably being skeptical. Maybe I'm being overly pedantic, overly concerned. Hawking himself realized this was a problem. In the original paper he wrote, he noted that the energy negative flux, the back reaction, over the horizon, will lead to the black hole not in fact being a stationary state. And because he observed this, he proposed a solution. It was a particular approximation regime, which I'll talk about in the possible resolutions. Now that approximation regime, I will argue, doesn't work. Otherwise there wouldn't be a problem. But until we get to there, even Hawking himself accepted that the derivation on its own terms doesn't work. Hawking's derivation is evaporation inconsistent. Am I doing for time?
You're great. You're 22 minutes.
Oh, fine. So, just to beat home the structure of this argument a bit more, here's what my argument isn't. A standard concern about modelling in physics would look something like this. I've done everything, assuming a black hole doesn't rotate. I've just written down Schwarzschild metrics. But we think physically realistic black holes do rotate. And so this sort of concern leads to a question, the idealization question. Can Hawking use his derivation, or one very, very similar to it, to derive Hawking radiation in curved black hole spacetimes? This sort of worry, this sort of de-idealization argument, is a worry about the truth of individual assumed premises, i.e. I've assumed non-rotating black holes. And de-idealizing means throwing away those assumed premises and seeing if the derivation still works. Of course, in the case of rotating black holes, the answer is yes. In the original paper, Hawking deals with rotating and charged black holes. And hello? Yeah? Maybe I clicked the button, I'm sorry. Did you all hear everything I said? Yeah. So I think the other examples of those sorts of worries are the Trans-Planckian problem, right? Which is a worry about whether the assumption of the Hadamard condition near the horizon is a valid assumption given quantum gravity. I take it that the answer is unknown to that idealization question. Finite infinity, what are the modelling infinity, the boundaries of the spacetime as being at infinity, you could bring into a finite distance, which is what we think physically realistic black holes should have. Like, we don't actually think that Schwarzschild is embedded in an infinite spacetime with nothing else in it. I haven't seen it in the literature that Hawking derivation being done with finite infinity, but I'm going to assume it's safe. I think most people certainly do. I know that, I stated that the in state is vacuum, people don't really think this, people think there's other stuff going on. And that in the literature has been worked on, and it seems that you still get something like a thermal spectrum, you still get Hawking radiation if the in-state is not vacuum. And finally, I think this is what the black hole information paradox is about. It's about whether we are right to assume unitarity or not, or global hyperbolicity, or one of the other thousands of derivations. They're about competing assumptions rather than anything really paradoxical. That's not what my argument is. My argument's about an argument style. You start with a spacetime, you derive Hawking radiation, you infer to another spacetime, and that undermines your own assumptions. So you've got not a non-valid, inconsistent argument style. You undermine your own assumptions. It's not just throwing away individual assumptions because of other independent reasons. The obvious thing to do is what I just did in the talk, is to ask if you can use the derivation from the new spacetime, and I've just argued that you can't, at least in any simple-minded way. So it's a concern about logical validity, not the truth of individual assumptions. Okay, and let's beat this horse a bit more. Friedenhagen and Hagen, the algebraic approach. We're going to go even faster. The way Friedenhagen and Hagen's approach works is you define a detector, and you put it on a Cauchy surface which intersects the horizon at the moment the matter crosses the Schwarzschild radius. And then you propagate the detector along the time-like killing vector fields in your collapsed Schwarzschild spacetime. So we're in collapsed Schwarzschild, and you're propagating, this orange region is collapsing matter, and you're propagating your detector along the time-like killing vector fields. And then what you find is you've got these two components on the Cauchy surface, which have two modes. One which can be put on the past horizon in maximum extended Schwarzschild, and one could be modelled on past null infinity. And as you propagate your detector along the time-like killing vector fields, these behave along the time-like killing vector fields, which are on these two horizons, rather the horizon and past null infinity. And so they get shifted infinitely close to the future horizon and to spatial infinity. And so you've got a contribution to the detector counting rate is given by modes increasingly well squeeze the future horizon and modes on spatial infinity. You ignore the spatial infinity modes and say they don't contribute anything because that's all vacuum. And then you find that assuming the Hadamard condition in the Transplanckian frequencies, assuming the Transplanckian frequencies look like the Minkowski vacuum, you find that there's a thermal spectrum of particles detected by your detector. This also fails in the maximal globally hyperbolic development of square minus. I just talked a bunch about propagating detectors along killing vector fields, which don't exist in the maximal globally hyperbolic development of square minus. You can't just not propagate the detector. The behavior of the modes is also defined by the behavior of these modes in the isometry with maximally extended Schwarzschild, which you also don't have. And finally, they take an asymptotic limit. They propagate the detector to t goes to infinity. You can no longer take t goes to infinity. T only goes to some finite value. So it just really quite obviously breaks down in Friedenhagen and Hagen. Friedenhagen and Hagen is more mathematically rigorous, and it's easier to state why it's inconsistent. It's an interesting point about mathematical rigor. Now the algebraic approach. In the crudest terms possible, you define an algebra of observables, and a state is then a function on this algebra of observables to the real line. And we demand that our state is vacuum. It's physical, which is Hadamard condition. And with this one, we don't demand that it's thermal. We've discovered that it's thermal. But a thermal state is defined by the KMS condition. There's a mistake on the slides, I apologize. So demand that it's vacuum and Hadamard. And you discover that the natural Hadamard vacuum state on collapsed Schwarzschild is the Unruh vacuum. The Unruh vacuum is thermal at the Hawking temperature, in the at modes, near future null infinity. It's just a result about a particular vacuum state on a particular space-time. I've thrown away that space-time, so that naturalness claim about a particular vacuum state on the horizon just doesn't apply. This space-time isn't even approximately the same, right? It doesn't have approximate time like kinetic vector fields. This space-time is describing a black hole being of mass m and then eventually being on Planck scale and being about to disappear. It's a totally different space-time, and yet the naturalness result isn't established. So they're both evaporation consistent. And I think the lesson of these three derivations is that in each case, because the derivation uses global space-time structure, and then we change the global space-time structure, they're rendered inconsistent, evaporation inconsistent. So let's talk about some possible resolutions that can be learned. Wow. Last talks, I'm going to finish a bit early, which is maybe a rest for everyone's brain. I gave a caveat about this early on in the talk, but lots of you may be thinking about your own favorite derivation of Hawking radiation. Anecdotally, talking to physicists and philosophers of physics about this topic it's really a Sisyphean task. Because you point out this paradox in these three derivations, and they just go, well, have you read this paper, which is consistent? And I go, I believe you, it may well be consistent. I mean, I haven't checked them all yet. But you haven't told me about what's going on with these derivations, especially the Hawking one. The Hawking derivation is what taught us in the first place that Hawking radiation exists, if it does. And yet it's evaporation consistent. How's that gone on? There's still a paradox for these historically essential strong, historically very important derivations. So even if there are evaporation consistent derivations, there's still a paradox for the ones I've discussed here. So let's think about that approximation regime that Hawking proposed that I mentioned. It's a sentence in the paper, and so I've tried to cash it out in the most precise way I can. Let's just think about how an approximation regime would work first. So you'd start with this maximum globally hyperbolic development of square minus spacetime. And you'd somehow say this approximates this spacetime somehow. Somehow this approximates this full spacetime. And because you can get this full spacetime, you then do the derivation on Clark-Schwarzschild. And then you infer back. You go, well, I approximated in that direction, and so I just infer that approximately Hawking radiation will exist on this spacetime. And Hawking motivates this by noting that for black holes with mass larger than the Planck mass, they're going to be evaporating incredibly slowly. And so you can say, well, they're quasi-stationary. They're basically stationary, so you can get maybe approximate kinetic vector fields, and then you get stationarity back and everything is well behaved. So what are these quasi-stationary states that we can find in MGHD square minus? Well, they're these. Black holes can't emit Hawking radiation from the horizon, because anything in contact with the horizon can't escape on a standard definition of a black hole. And so Hawking radiation has to be emitted from just outside the horizon and then escape to future null infinity. And the way you get a black hole evaporation is you have a negative energy flux going back over the horizon. So you've got these sort of positive and negative energy flux emission events, which creates black hole evaporation. And this is I've basically taken this diagram from Ward, so I haven't pulled this out of thin air. This is how things are often modeled. And so you can imagine this Hawking radiation carrying away a bit of mass. And so just after this emission event, the black hole is going to look like it's stationary until another emission event, where it looks to all the observers in this region that the black hole's changed mass. After that region, the black hole's changed mass. So in those ticks, the black hole looks like it's got a constant mass. Everyone agrees that it's mass m. And so these regions are approximately isometric to a similar region of collapsed Schwarzschild. So there's also going to be a tick region going over the horizon, and going up to feature unflinching collapse Schwarzschild, which you could say is approximately isometric to that tick, right? And so you go, great, so I've got my approximate isometry. But we didn't derive Hawking radiation in one of these ticks. We derived it in an entire space-time. And the way to see this is, this tick doesn't intersect the collapsing matter at all. And so it only goes along a tiny bit of the horizon. Indeed, if you're on future to infinity and propagate back, you don't get particularly close to the horizon. And so you can't carry out Hawking's derivation in one of those ticks. You need to infer the entirety of collapsed Schwarzschild. You need the entirety of that structure, including the collapsing region. And these ticks aren't Cauchy. They're not Cauchy is defined by every inextendable causal world line intersected. Here's a bunch of inextendable causal world lines which don't intersect it. In fact, that tick, its past domain of dependence, doesn't extend beyond that region. You get none of the past structure back. So Hawking's derivation is a global, at least Hawking's derivation of Hawking radiation uses the global structure of space-time. And you can't recover it using this approximately isometric region. So your approximate isometry doesn't get all the structure necessary for Hawking's derivation. And so without all of that, again, the derivation doesn't work. I don't claim to have exhausted the possibilities of Hawking's one sentence in 1975 about how approximation machines might work, but I take this to be the most natural interpretation of how it might work, and it doesn't work. So, the next, I call this the implicit structure proposal, and I think this is probably what's actually going on. So maybe both of these spacetimes encode some sort of local structure, and it's that local structure which really gives rise to Hawking radiation. And so even though the global structure is different, they've got the same local structure. And a potential proposal for this is a Matt Visser paper in 2003, which he calls the essential features of Hawking radiation. But there's a bunch of open questions with this proposal. Firstly, what is that local structure? And how is it being encoded by the global structure? Then how is that local structure getting us Hawking radiation? And is it giving us the same thing? Is it still thermal? Right. Is it, I mean, just to take Visser's paper for an example, provides a thermal spectrum in the two-point correlation functions, which is maybe a slightly technical thing to say, but the Unruh effect also has a thermal spectrum, but it doesn't have any time asymmetry. You don't have that past vacuum being an energy flux being emitted by the black hole to feature infinity. There's just a thermal bath everywhere. And so, has this actually derived Hawking radiation, or has it just derived the Unruh effect? Right? So you have to make sure that our local derivation is still deriving Hawking's effect. And if it isn't, maybe we're learning something about the nature of Hawking radiation. Maybe we were just wrong to think it was thermal before. There's a lot of lessons to be learned. It certainly has, this project hasn't been carried out, right, is my claim. But this is a possible resolution. Naturally, you might think quantum gravity is the way to go. Black hole evaporation, deep down, fundamentally, is a quantum gravity phenomena. And so maybe the way to get rid of this paradox is to just, we're going to need the proper full quantum gravity description. But I don't think this can work. And the reason is, if you're going to describe evaporation, then in the semi-classical limit, you need to be describing a black hole losing mass. If you think once we have a full description of quantum gravity, we don't have a description of black holes losing mass, then I put you into section 6, evaporation skepticism. I think you're doing that. So I think a minimal condition, a necessary condition for describing black hole evaporation is mass loss. And as soon as you have mass loss, you have a failure of stationarity, and as soon as you have a failure of stationarity, you have a paradox in these derivations. And so I claim that the paradox arises far before the Planck scale, for the evaporation event. As soon as you have a black hole changing mass, you've got a paradox. Maybe it's something, this is radical philosophy of science type stuff now. Maybe there's an essential idealization going on. There's a lie in the way we do physics which can't be removed. It's just inconsistent. Now, as I mentioned, there may be consistent derivation, so we're not going to say that Hawking radiation involves an essential idealization simpliciter. Maybe we can say something weaker, maybe a weak essential idealist claim, essential idealization claim. It's that there are both consistent and inconsistent derivations, and physics has or must use both sets. And there's no way to resolve the inconsistent derivations. We learned about Hawking radiation through an inconsistent, essentially idealized derivation, and it just doesn't have a resolution. That's the way physics works. Slightly radical epistemology, but some people might want to defend that. Finally, we can be evaporation skeptics. This is going to run hard against a lot of the physics community, but you just reject that the back reaction arguments are good arguments. There's a lot of open questions if you have to do this. What exactly goes wrong with the back reaction arguments? And how, do you have a drastic violation of energy conservation? So open questions to be answered. Or you could just be skeptical of Hawking radiation. And I take this to be, when I say, I just think this is implausible. You've got a lot of consilience from various different areas for the derivation of Hawking. We've got a lot of consilience motivating Hawking radiation. And the paradox only gets off the ground once you've got that derivation, once you've got evaporation. So if you just reject evaporation, then Hawking's derivation is still a good derivation. And so it seems too strong to reject Hawking radiation outright. So, what do I want you to take away from this talk? I want you to take away that there's a paradox to be resolved. There's a genuine, inconsistent argument style which hasn't been explained how it's working in the literature. It applies to multiple important and rigorous derivations of Hawking radiation, and hopefully, just to steal Wallace's quote about the information paradox, for my own purposes, we find ourselves in the enviable situation of having an interesting problem with no really satisfying answer. If we are lucky, this means we'll learn something deep. Thank you for your attention.
Thank you very much, and we'll turn it over to Saakshi Dulani for the comment.
Thank you, Dominic. I think that was a really well-structured presentation and argument, and I just think it's very valuable to the literature because in my own experiences, just asking, physicists and philosophers how much they care about the question of space-time structure when thinking of black hole evaporation, the responses run the gamut. And Nick, this time I got that word right. This is a joke from before, but where either you have to be extremely worried about it, or, which tends to be the more common response in physics, I think we can be safe in the ignorance is bliss attitude. We won't really know until we go into more details into some quantum gravitational explication of black hole evaporation. And I think what you did, where you acknowledge, there may very well be evaporation consistent models and derivations out there, but the important part of what you did is saying, we need to be able to vet those proposals and understand what exactly they're solving. So by making the inconsistency precise, we can do that. So I, very much appreciate your effort in that. I depart from your argument in terms of the optimism about the resolution. And so for my comments, I would really appreciate for you to go to the slide where you have the really nice schematic of the non-evaporation Penrose diagram leading to an arrow of the fire, leading to an arrow, the evaporation. Exactly, yes.
A black circle with a fire. It's what
Okay. So I think this is a really nice visualization of what the argument is. We start off with Hawking radiation. We think that implies black hole evaporation. We have the assumptions that go into the derivation of Hawking radiation, and that arrow leads to the black ball with the fire, and then we use that step to infer that we have an evaporation space-time. But it seems like the evaporation space-time then negates our initial assumptions. So I just want to go through different ways in which you might want to resolve this paradox, and why I think there might at least be scope for more optimism than what you seem to imply towards the end. So of course, the first thing you can do is change the initial assumptions, what you called the properties of the space-time, and it seems like the most promising way to do that is to make them much weaker, right? Of course, stationarity can't be part of your original assumptions, and something along the program of Visser seems to be that we're really gonna not say much about the global structure, and it seems like from our discussion, Parekh-Malik's derivation could be an example where, because that derivation tries to, give a dynamical story about, the tunneling effect, what you were talking about briefly in terms of the positive and negative energy fluxes. We could be pretty agnostic about what the global space-time structure will eventually look like in the evaporation case, and we might be able to complete that circle. Now, you're saying that that's not satisfying to you, because even though we have a consistent derivation like that, perhaps, it doesn't negate that this still fails for, let's say, Hawking's original derivations, or one of the examples you went through. And my question is, I think it does resolve the idealization paradox. You seem to be invoking another meta-level paradox in mind, that so long as we have these inconsistent derivations, we have to ask a philosophy of science question: why could we learn from them what we actually did? Right? There's this concern that we seem to have believed in Hawking radiation because of these derivations in the 1970s, that now we don't have reason to trust anymore once we realize that they're inconsistent. And I guess I'm a bit puzzled as to why we still have to insist that we learned about black hole evaporation from these 1970s derivations. Why can we not say we learned about Hawking radiation as a kinematic effect, basically block the inference from Hawking radiation to black hole evaporation in these problematic derivations, and say we needed to go to alternative derivations to complete the loop to learn about black hole evaporation? So that would be my sense of how you could be happier with using alternative derivations to say we still learned something important about black hole evaporation, even though originally we learned about Hawking radiation as a kinematic effect from what ultimately was an inconsistent evaporation spacetime. The other way you can go is not to outright be an evaporation skeptic, but you can just say that really our reasons for believing that Hawking radiation leads to black hole evaporation does require quantum gravitational machinery, right? We want to be able to say that the black hole is some sort of macroscopic system with microscopic constituents, and we see these microscopic constituents that are eventually radiating away. And while you don't necessarily have to be an outright skeptic in terms of rejecting the back reaction arguments, you can say, well, that leads us to question this evaporation spacetime diagram that Hawking gave us, that's very ad hoc. And at least in the information loss literature, that's of course one of the first go-to moves, right? We say something is wrong with this diagram. We're gonna radically, change the problematic features of that diagram. And then we reverse engineer the Hawking radiation part successfully, which is what we couldn't do with this particular diagram where you have the X. So that seems to be another avenue to resolve the paradox. So now my question to you is, given these two ways of dealing with what I think is a very important articulation of what we need to pay attention to, where is your continued skepticism or dissatisfaction that these are, from an epistemological point of view, we can say that we can truly make progress by attacking the premises in these ways?
Great, thank you. I'll make a general comment first. I am sorry if I came across as a pessimist. I'm not. I think there is a resolution to this paradox. Specifically, I think it's an implicit structure resolution, like you gave, right? I think you pointing to the tunneling derivation is an instance of doing a derivation with some sort of local structure. What I'm saying is there's a bunch of open questions about how that actually works, right? Like how are these spacetimes encoding that local structure? And then do we still get Hawking radiation proper out? Is it still thermal? Does it still exist? Is it, yeah. All of these open questions, which I think, trying to figure out how these derivations encode that structure will teach us something. And I think in your first proposed resolution, you seem to be suggesting that we don't need to figure out those open questions. I mean, you're shaking your head, so maybe not. But I think we learn about black hole evaporation through the existence of Hawking radiation and back reaction arguments. And so if we get the existence of Hawking radiation from Hawking's original derivation, then somehow that's latching onto the existence of Hawking radiation. So I think it's just part of the reasoning to black hole evaporation. And if we want to understand how our modeling in quantum field theory of curved spacetime is working, and what Hawking radiation actually is, if you want to say what Hawking radiation really is a quantum tunneling effect at the horizon, right? Then if you can show me that somehow it resolves this paradox, then I'm like, great, that's a better picture. I then reject Hawking's picture, which is that what Hawking radiation is a propagation of a past mode through a collapsing region onto future mode. They're different stories, right? And you said Hawking's is wrong. This is how Hawking's derivation actually latches onto the real structure, right? And the heuristic picture Hawking gave was we've learned that that's wrong. We've learned something from the idealization paradox. I think that's a really plausible thing for like this research project to lead to. I'm just saying it needs to lead there. It hasn't been done. In terms of your second proposal, which is to question the evaporation diagram, I think I can say something more concrete, which is I don't need this particular version of black hole evaporation. The first thing to say is any realistic, plausible, not draw an extra triangle on top and then carry on with your day approach to evaporation diagrams is still going to have non-stationarity. It's still not going to have time-like kinetic fields, obviously, the black hole's losing mass, right? And so they're still going to break down, right? And in physically realistic evaporation models, which are done with numerical relativity, even more structure breaks down. And so in an evaporation spacetime, the event horizon is no longer time-like. No, it's time-like, it's evaporating, right? And so it's not just that the null vector, which is parallel transporting along the horizon, is now going to be changing. It's no longer going to be null, right? It's like, and so more, I think with physically realistic evaporation models, more stuff goes wrong. And so I don't think complaining about this quite naive diagram that Hawking wrote down in 1975 is sufficient to resolve the paradox, because more robust approaches, the paradox is still there.
Yeah, sure. Go ahead.
So I agree with everything you said, and I just want to clarify where I'm actually disagreeing. So I'm definitely not denying that enough work has been done about the first strategy of implicit structure, it seemed to me that you were saying even if enough work has been done, even if we flesh that out, there would still be a problem, because now we're saying that there's another physical story for Hawking radiation that we were giving, and it doesn't explain why Hawking's original derivation should have been trustworthy in the first place. And to me, that's a philosophy of science question, and you're calling that it's still paradoxical. So I'd appreciate you clarifying what I'm interpreting as a meta-level paradox you seem to be invoking here. And then for the second strategy, I definitely do not mean to imply that if you're going to, change this diagram in any meaningful way, like getting rid of stationarity, you're completing the loop to the left. What I mean is you're cutting off the loop to the left, you're just reverse engineering, the Hawking radiation. So that point is well taken. I'm interested in your philosophy of science worry that we seem to be doing physics with consistent derivations and inconsistent derivations. And my question is, why do we think we have to be holding on to the insistent derivations to be doing that physics? Where resolving the paradox means we are now, in some real way discarding the inconsistent models, but we can say what we've learned from them, and that's the suggestion I gave, as Hawking radiation as a kinematic effect, but of course we needed to do something radically different to learn about Hawking radiation as a dynamical evaporation effect.
That's really helpful. Yeah, I agree. If you have a story about how Hawking's derivation latched onto some evaporation consistent derivation, which we think is actually going on, then you don't talk about, then you rendered Hawking's derivation consistent, right? And so you don't have that essential idealization picture this comes about if you don't have those stories, right? So you can't render it evaporation consistent, it's just fundamentally inconsistent. I talk about, in the paper, I talk about multiple realizability, but I won't go into that. There is then an interesting philosophy of science question, which is, well, suppose we get this done in the next few years, then we've understood how Hawking's derivation latches onto the true nature of Hawking radiation only in 50 years after he actually wrote it. Why have we believed it this long? And I think that's a really interesting question, both philosophy of science and sociological. I think the main thing is consilience. The picture of black hole thermodynamics you get once you believe in Hawking radiation is really beautiful, and you get, it sort of fills in the gaps of Bekenstein's work. And yeah, so I think it's going to be some sort of consilience argument more than anything. And then especially once you start getting other derivations, some of it trying to be consistent, you go, these seem to be latching onto the same thing. So you now have loads of different derivations. So it's going to be sort of Hawking's derivation was situated in an inductive world which gave us more credence for Hawking radiation over and above just Hawking's derivation. Right? So I'd say that's an important part of why we still believe in Hawking radiation despite this. I just think there's still lessons to be learned by pointing this out. Your question had a second part, and I've forgotten it. So.
I think what you said was excellent. I'm happy to open the floor.
Thank you very much.
Yeah, and I've had several people catch my eye, so there's a few people in the queue already. I'll add you, Wayne. Jamie was first.
Yeah, I think had a clarificatory question that was similar to what Saakshi was saying about that loop. And I think, in some ways, I think you've kind of answered it now after the sort of back and forth that just happened, but I kind of want to, give my own sort of way of saying it to see if I've kind of understood how this goes. So when I think of self-undermining arguments, I think of situations where you start with a set of assumptions, you prove something with those assumptions, and it turns out to be inconsistent with the assumptions you started with, so there's some kind of instability with the starting set of assumptions. And so it seems like in the situation you described, it's true that you don't have a convincing proof of Hawking radiation or derivation of Hawking radiation, But what you have learned is something about the instability, about the starting assumptions, right? And so that tells you something about the space-time that you started out with. And so that seems like it's still kind of meaningfully helpful in thinking about why we would have learned something to do with Hawking radiation, even if it undermines the sort of derivation on the basis of those assumptions. And so I guess my question then is, if that's the right way of thinking about it, and I think maybe this is what Saakshi was getting at, why don't we think that the right response in that situation is to say, okay, there was this derivation, we don't think it's any good, there's something self-undermining about the assumptions we started with, so what we need to do is we just need a new derivation. And so why isn't the correct response just to say, well, we don't need these inconsistent derivations after all, and maybe the correct way of looking at the derivations is not as something we need to try and fix, but as something that's kind of historically interesting, maybe gave us a guide towards the derivations we should actually be paying attention to.
Yeah, I first think you summarised the learning about space-time well. I think that's right. Maybe it's. I think if there are these inconsistent derivations, which historically, as a matter of fact, did teach us about Hawking radiation, and yet we think they're inconsistent and maybe have an essential idealization involved. Like, that's really weird. That's incredibly weird. Like, we learned about our world using models which cannot be made to accurately describe our world. It's basically what we're saying. And people like Bob Batterman think that there are essential idealizations, and they're just going to say, yeah, we model with we use models which lie, and that's just the way physics works, and that's sort of the essential idealization part. But I think that's quite a radical proposal about epistemology and philosophy of science, and I think what's more likely is that somehow Hawking's derivation latched onto some other structure, which is actually Hawking radiation. I think that's probably what's going on. And if we can learn that, I think that'll be very revealing for how modelling in quantum field theory and space-time works. I think when you read the general relativity text by Ward, it's all defined globally, right? And so there's a open question about how that's encoding local physics, what that question is. And I just think this is a pathway into that question, and just throwing out Hawking's derivation, going, oh, it's inconsistent, let's just throw it in the waste pile, I think misses this opportunity to learn.
Yishin.
Yeah, thank you for the great talk. I really like the style of what's going on. Can we go back to the possible resolutions? Just a short comment then. Yeah. I think first of all, I want to, like, there are two things, right? First, the radiation, and second, evaporation. Radiation is well taken, and evaporation is the thing, like at the heart of this discussion. And here, my attitude is simply, I think I definitely take 3 and 4 on the par. Like, I think they are similar things. So here's the reasoning. Let's focus on evaporation. I think I almost agree with everything you put in the argument. And the basic ingredients in Hawking's argument contain 2 parts, right? The first is the global structure, hyperbolicity and the asymptotic flatness to guarantee the energy conservation. So far, all good. And the second part is his consideration that because in GR, in classical GR, and from the global perspective, there is nothing can stop the negative flow of the creation of particle into the horizon, so that the decrease of mass will keep going, and nothing stops that. So in order to prevent to be a negative mass, it should evaporate. And the second ingredient, I think, is the crucial one, because like to be more charitable, if we are in 1970, and we are Hawking, we are like have a good understanding of GR, but nothing like and also like the semi-classical derivation. But we really don't know the local degrees of freedom and the local mechanism, and also the mechanics of singularity, which is not shown by GR, right? And that's the thing about the three, right? I totally agree, because the quantum effects already will happen in the regime, in the neighborhood of vicinity of event horizon. And then the dynamics of a singularity, as I mentioned, is also part of the story. It concerns the quantum gravity. So I think 3 and 4 should be considered together. And then if you consider that, one possible thing in my mind is the remnant, right? If Hawking has the knowledge, or in that at the time, you have different versions of quantum gravity, or not even like remnants. You can also think of a fuzzball model. Like those are singularity resolutions, and it provides you some kind of mechanism to stop negative mass. Apart from from the perspective of global topology, there's nothing. You do have something to help you to understand what's happening if the decrease of mass approach to the limit, right? And then you do have a better understanding of the physical picture behind, and this renders Hawking's derivation, and the derivation is, as you show here, is a problem only if we stand at the point from the point of view of classical GR, and we really don't know what's going on in the local region and the quantum gravity region. So that's my short comment. Yeah, Bob.
Thank you. It's super interesting. I think the first thing you said I'd push back on a bit with sort of remnants, because I tried to emphasize that I think the paradox arises quite a long way before the late stage evolution of the black hole. I think it arises once you have a black hole losing mass, which a remnant isn't going to help resolve on its own. You then mentioned, and correct me if I mischaracterized you, but maybe when you get the story of remnants, you're also changing the story of how evaporation is working a lot earlier on. And so maybe in those early stages of black hole evaporation, where the black hole is just losing mass, quantum gravity can give you a different story then. I'm naive to those sorts of proposals, maybe. If you can then get a different derivation of Hawking radiation and run an implicit structure style argument with a quantum gravity description of Hawking radiation, then I would agree it's an implicit structure resolution. I guess what I have in mind more with my pessimism about quantum gravity as I presented it here is we normally think that semi-classical gravity on curved spacetimes is a good modeling regime, an accurate modeling regime, until the late stage evolution of the black hole. And therefore, my naive thought is that we would expect any theory of quantum gravity up until those Planck scale black holes to recover that in the limit, and in that limit, the paradox arises. And so that's a very naive way of saying why I don't think quantum gravity quite is going to get to the resolution, but I accept it as an open possibility that there's a way to do quantum gravity on an implicit structure style derivation, which is going to get you there. It just has to do it before, a long time before the evaporation event, when we think quantum field theory on curved spacetime is a good modeling regime. Does that answer your question?
Yeah, I think that's helpful. But just to clarify, I think as you said, quantum gravity effect happens at the late stage of the evaporation. I'm with you. So to say that the semi-classical results should be fine in the early age. No, that's my last comment on that. Thank you very much.
Okay, so everyone wants to get into this discussion, so unfortunately that's not possible. I have a queue, and Sean is next.
Okay, thanks. I really glad that wow. So first, great talk. I loved it. Really interesting. Second, I'm totally on board. I completely agree with you. Also, I've been worried about I'm glad you put this together really nicely, because I've been worried about a version like this for a long time. I do think that part of the reason why it comes up as a paradox in the way you say is because you black boxed these derivations. And I think that we can possibly learn something by opening up the box a bit and thinking about actually what has gone wrong and how we can modify these derivations. I don't think it's that hard. So, for example, like a lot of the work of the Hawking derivation goes into deriving the thermality of the spectrum. That's where a lot of the hard work goes into. But actually, so if the radiation is not thermal, it can still be carrying energy out to infinity. That's not the problem. So if you're worried about whether the black hole's evaporating or not, I don't think that's really at issue. It's whether the radiation that gets out is thermal. Doing that calculation is not that hard because Bogoliubov coefficients are messy to calculate, but they're not hard to calculate. It's simple. In principle, it's a simple thing. You could probably do it numerically. And one of the things that I worried about was like, how do you know whether the black hole starts evaporating too fast for the radiation coming out to thermalize? And what would that mean for the things like the information loss paradox? Because if the radiation is not thermal, it might contain some information. And so like I asked around, like, who's done this? Because I think the question is like, where is the Cauchy horizon? And like the observers, like the fastest time-like observers, where do they intersect that? Because that's going to be the pure, the most thermal radiation. And I was like, that should be a calculation that you can do if you kind of know, if you have some like idea about how you think. Anyway, I asked around, I don't know. Like Eric said he didn't know if anybody's done this, but I'm like curious, does anybody know? Like, no. Anyways, this is what I would want to do. So, but I think that the paradox is hinting at like the nature of the radiation rather than whether the black holes evaporate or not. And that's just, I don't know, I wonder what if you...
I'm incredibly sympathetic to everything you said. I think one of the very plausible lessons we could learn from like paying attention to like making sure our derivations of Hawking radiation or evaporation consistent would be losing thermality. I think that's very plausible. I think you still then want to, as you say, tell a story about what Hawking radiation is, like get that insight. I mean, I think one of the things you learn by paying a close attention to these derivations is that the story Hawking told, it just isn't the right story to tell, because everything in Friedenhagen-Haug's derivation, for example, happens outside of the collapsing matter. Right? You draw this Cauchy horizon and do everything on that and beyond, right? And so that intuitive picture Hawking gave of having stationarity, non-stationarity, and that particle creation seems to be weakened, and that maybe having that sort of space-time structure is going to be a necessary condition for Hawking radiation, but we don't think necessary conditions are that strong for understanding of phenomena, and much more what's going on is, as sort of we talk about, is the clumping of modes being stretched, right? And so we're paying attention to how to make derivations more or less evaporation consistent. We learn about what Hawking radiation is. We learn about how Hawking's derivation latched onto what it is. We learn about what actually is coming out. So I totally agree, these are all lessons we're going to learn. I just think this is a nice way to do it.
Yeah, no, I agree, and I'm going to just like, the value, I think, of this work is to push people to adjust the derivations to kind of be more consistent.
Yeah.
Then I think we could learn something really interesting about this.
And Saakshi wanted to jump in on this. Yeah.
I don't know if this answers your question, Sean, but I think the question of thermality is intricately tied to what you think the regime of validity of semi-classical gravity is, at least a certain understanding of what semi-classical gravity is. So I know in Maulik's derivation of the tunneling, he actually says that it's not exactly thermal, it's very close to thermal, but he takes that as an indication that you could, consider a way to, get information out. But I think that relies on other background things going on. And this is the follow-up I had for Dominic earlier, you seem to say that the strength of your paradox seems to depend a lot on how long you can use certain semi-classical tools, which is why you say that, really up until the Planck scale, we should be able to recover a semi-classical limit. And I think that's exactly the contention, is what are the boundaries of semi-classical gravity? How are you defining it? And so if someone were to respond being like, hey, in my derivation of black hole evaporation, what you think is semi-classical gravity breaks down way, way earlier than the Planck scale, what would your response be?
Yeah, I mean, I said on the first slide that I build my paradox by assuming all of this standard modeling stuff is really good, including back reaction. And that might not be true, right? Making derivation consistent might teach us that the standard modeling framework of quantum field theory and curved spacetime in semi-classical gravity breaks down really early, right? That's a super plausible lesson. I don't think it would be a problem for me, because the interesting question would be then to be, well, what do we have to change about Hawking's radiation? What is it, Hawking's derivation and Frieden-Hauenhaus in the algebraic approach? What did they get right? What did they get wrong? What is Hawking radiation actually in this new non-semi-classical gravity picture we tell? And so, yeah, I think that's a totally plausible way to go. But again, it's I think, slightly more radical than some of the things I'm saying, right? It's like all of this good work on semi-classical gravity, which I treat semi-classical gravity for a long time until Planck scale physics. Oh, that's all wrong. Which, I think there are slightly less radical things to say first, and so there's a large possibility space to be explored. Yeah.
Okay, I have Raymond and then Wayne, so go ahead, Raymond.
So I have a few thoughts, so I apologize if this is a bit of a ramble. But I kind of want to take a step back here. In particular, one thing that came out a lot was the fascination of the question, why trust Hawking? And I think that's a really interesting question, and I kind of want to connect that to a theme that's been going on in this talk for a little bit too, and that's the question of whether this current episode in physics is unique, or, and I think someone, I forget who, I think it was Wayne actually, who said it's always been thus. I think that's true here too, because we can connect, I think, what's happening here with an episode in the history of physics, in particular Galileo's derivation of the speed of falling bodies. Like, we learned from Feyerabend and to Margender that his reasoning there was invalid. It was famously invalid. And recent work by, I think, Stewart argues that Galileo nonetheless had a certain imagination involved. And for reasons of consilience too there, we had reasons to think that Galileo was latching on something true, about relativistic Galileo space-time. So I guess I'm making this connection to contribute to a level of optimism again. We're not in a new place here, despite this seeming, paradox of derivation, which I take on, as you're saying, is like a legitimate one. But we've been here before. I have faith we can do it again.
Yeah, super nice connection. I hadn't drawn that, but yeah, it's nice to think about. I agree, similar to Galileo, there's going to be nice philosophy science questions to answer about what was it, despite the invalidity of the reasoning, which makes us still believe it, and you're going to draw out lessons about what it is that gives us confidence in particular statements in physics. And there probably are a lot of parallels with what happened in the case of Galileo. I just think that slightly more specifically, the optimism is about, and as Sean said, learning something specific about Hawking radiation, about semi-classical gravity, about black hole evaporation, right? Making our reasoning consistent will teach us something beyond philosophy of science about the actual physics.
Sure, go ahead. So just one quick comment. The parallel might be for Galileo too, how much do we want to precisify Aristotelian physics? According to what you were just saying. I think
semi-classical gravity on curved spacetimes from the 1970s onwards has more reason to be taken seriously than the simple Aristotelian physics.
Of course.
And so there's more to learn by like thinking about how this physics, which we're still taking very seriously and is informing empirical work now, can be rendered consistent.
I have to recommend a paper by Carlo Rovelli on making precise Aristotelic physics, by the way.
Go ahead, Wayne.
Thank you. This was very thought-provoking. I'm playing my role once again as outsider's perspective. My reaction is the move that Hawking makes of appeal to quasi-stationarity strikes me as along the lines of very standard things that people do in physics, and my worry is that the sort of worries you raise could actually apply to lots of things. And here's an imperfect analogy. Suppose I want to use quantum field theory to analyze a scattering experiment at CERN. First thing I'm going to do is I'm going to put in Minkowski spacetime. I'm going to analyze the in and out states as free fields and get particle content out of that. Don't worry about whether I can talk about particle content in the interaction region. And get my scattering amplitudes. And then someone comes along and says, well, first of all, asymptotic infinity doesn't exist. These fields are never free. And hey, you know what? They're not in Minkowski spacetime. CERN actually is on the surface of the Earth. It's in a curved spacetime. And it's not a stationary spacetime, so you can't rigorously define those in and out modes. And the standard response is, shut up. It doesn't matter. Like, the idea is that on the time and distance scales that in the scattering region, it might as well be in Minkowski spacetime, so we can use the calculation in Minkowski spacetime to get a good approximation to the real thing. And my thought about the Hawking thing it seemed to me that this involves a sort of separation of time scales that people use all along. So sure it's losing mass, right? But I would expect that on the time scales relevant to particle production, that rate of, as long as we're not in the late stages, that rate of loss of mass is very slow. And so things are going on the near the event horizon, I would think. On the time scales relevant to particle production, the lack of stationarity doesn't matter, and also the global structure of space-time doesn't matter. And I just downloaded the paper, and I find that Stephen Hawking agrees with me, because he said he explicitly invokes separation of timescales. You know, he says the negative energy flux will cause the area of the event horizon to decrease, and so the black hole will not, in fact, be in a stationary state. As long as the mass of the black hole is large compared to the Planck mass, the rate of evolution of the black hole will be very slow compared to the characteristic time for light to cross. Right? Yeah. Right. Yeah. So I'm reading that, and then the next sentence. So why doesn't that separation of time scale argument work? What? You know, I'm using. I know it's not a stationary space-time, right? But why shouldn't I think that on the time scales of relevant to particle production and time and distance scales, that what happens is not going to be sensitive to that slow change of the space-time, and also not be sensitive to global structure. Again, you know, this doesn't apply to the late stages. I think you're right. Late stages, all bets are off.
Yeah. Thanks. I think you're right. This is the physics intuition. It's frankly my intuition, and that's what I think happens. The first thing to say is this is a different, I try to emphasize this is a different sort of thing to those standard idealization worries, right? So let's say QFT on curved spacetimes. Not QFT. QFT standard, QFT proper, particle and annihilation creation with Feynman diagrams and whatnot. We use infinity, but we think that's just an idealization, and it's a false assumption. So we think, if we throw away that assumption and just model large distances, and large distances here are like a few meters in the countryside in CERN, do we still get approximately the same results? And you can take limits, you can do this precisely. There's a literature on this sort of thing, and presumably the answer is yes. So you get rid of that false assumption, and you still get the results approximately. And this is the sort of thing we do in standard literature on idealization, right? We don't really believe there's an infinite amount of water in your kettle to get the phase transition. If I just take n becomes very, very large but finite, do we get something that looks like a phase transition? People argue about this, but most people think yes, we do, right? Up to some epsilon. I argue that this is different because your argument undermines your own assumptions, right? This is why I emphasize this isn't about particular assumptions which were rendered false. It's about making your own argument for the conclusion invalid. And that's relevant because I think in the story you told, there's an implicit resolution which you go, really what Hawking radiation is, it's a local phenomenon which happens at the event near the horizon, which is insensitive to the long-term periods of stationarity. I'm like, sure, you show me what that is and tell me how Hawking's derivation, which doesn't do that, latches onto it. And then I just say you've resolved the paradox, right? I think that is a plausible way that things go, but you can't just derive Hawking radiation with a lot of global structure, change that global structure, and then say, there's a different story which I haven't written down, but that's what's really going on. I want to know what that story is. I want to learn about how the global structure is encoding that story. And so I think the story you told is probably, I mean, I wrote in the bottom right, I think that's basically the way to go. I think it's to find a local derivation. I just want that to be worked out, and not just assume that it's there.
Okay, I know there are a lot of other people who wanted to enter the queue, but I think we should maybe stop the discussion there, and then we're going to shift very briefly to some closing remarks from Nick Huggett. Oh, and let's thank Dominic before doing that. Oh, and Saakshi, yes, thank you both. Yeah, that was a wonderful discussion, and so I want to endorse what Chris said, that Nick is really the chief organizer for this event, and so I'm going to turn it over to him for some brief closing remarks. No pressure, though.
Well, let me see. I'll make some closing remarks, and then we'll come back and maybe do some real thanks, because there's other people here who still need to be thanked. Okay. Well, at the risk of lowering the tone after that the amazing discussions we've had this morning, I just a few brief thoughts. So one is, this is almost 4 years ago, the four of us were 4/7 of the organisers for a conference in Abu Dhabi, which was kind of bookending the current project that Chris and I have been on. And a few, Mike and Niels, were you there, Adam? Okay, yeah. Turns out I've got very bad at remembering who was at what things. Anyway, so if there were others here. And that was really nice, and I'm just really happy to kind of come back and that we ended up doing this again here, and what a fantastic kind of meeting this has been, and I've really kind of enjoyed. I mean, I guess it's admitting to my age that, especially there's so many kind of younger people coming into the field, and just the quality of discussion that we've had from everybody has just really made me extremely happy for the state of the field and what's been happening in the last few years. So actually, I guess I was going to say, since there's quite a few of you in the room, not only was there that meeting, but quite a few of you we also met online a few months later in the summer of 2020. I think maybe half the people here were involved in that sense. I remember you sitting in your garden in Italy with somebody hanging laundry out behind you.
Oh my God.
Okay, so great. I will say so that's the thanks I have now to everybody who's been participating. I mean, everyone's been really engaged, and it's just been great. I've had a really terrific weekend. So just some sort of thoughts to sort of try to, summarize or bring together everything that's sort of been happening. I mean, all the talks were amazing, and I learned a great deal from all of them, and really wanted to talk about all of them. I think there's various different ways of kind of cutting them up and relating them, but here's sort of one thought that maybe helps, at least helps think about the way I've been thinking about it. So yesterday, I think Raymond asked about how philosophy had been sort of influencing the physics, and maybe in particular I don't know, did you ask about the creativity, or that kind of came up? So that was we had some good comments there. But I did want to kind of also flip that around, and for thinking about what's going on here, the immense value of kind of how the physics is influencing, I think, the philosophy, and sort of just think about ways, just be aware of that sort of happening here as well. So thinking about how the philosophical content of the talks, whether they're by physicists or philosophers today, and I think how they, help advance philosophy of science in various ways. And I guess, just to sort of organize the talks a bit, I think I see it in sort of two main, you can see this in sort of two main ways. So one, which is sort of the majority of the talks, has to do with I would say, sort of relation between theory and experiment, or knowledge and experiment more generally. On the one hand, we have the talks that are really thinking about, the nature of experiment and the philosophical problems of experiment, and I think, help us understand that. So there was, talks about dark matter and the Hubble tension and LIGO and the Event Horizon telescope. I wasn't supposed to start with those, but so I'll come back to. Okay. On the other hand, I think, still with an eye to experiment, but leaning more to the sort of theory side, there was, the talk about inflation and the sort of whether we can understand that as a theory, even as an effective theory. And I think Faraz's talk as kind of as well as on the theory side, also thinking about connecting to what we have, what the phenomenology that we have. I actually meant to sort of start with Mike's talk kind of at the top, which is really the one that was most directly trying to bring those sort of two things, I think, sort of together in a kind of general theory as well. So obviously I was writing these notes during Dominic's talk, and I was like, oh, this doesn't fit in very well. But it's kind of in the middle as well, I think. Chris Mitch sort of yesterday thinking about, you were quoting me, I guess, me and Craig, but you made sort of the point about trying to think about the intersection of GR and quantum, and of course this is exactly why black holes are sort of so important as, quasi-phenomenology here as well. So I sort of put that there. So I think, when you're thinking about the sort of details of the physics, and it's cast into a story that's thinking about how we can use the experiment inductively to think about theory and what it is exactly we've learned. And of course, those just are the central questions of philosophy of science, I would say. The other sort of set of talks that Sean and Lee's and Luca's talk, a little harder to fit into that perspective, but I think Amelia in her comments to Lee kind of also gave us a kind of way of thinking about one central sort of philosophical way of thinking about what's going on there, which has to do with, the role of kind of principles in advancing science. That was in response to Lee. I think, obviously, that's very first, was it Deleuze you were kind of quoting yesterday? Right. You're saying it's very first, front and foremost there, but also very, clearly in Sean's talk with discussing about sort of symmetries and how that relates to measures. I think, I mean, I think it's in the background in Luca's, I think Daniele Arritti has kind of, emphasized the principle there is the thought about sort of hydrodynamic kind of analogies and taking those kinds of limits, I think is what's sort of in there as well. But that's sort of sitting back and then sort of thinking about, principles, again, is sort of a kind of classic philosophy of physics kind of question. I mean, I would say, one issue we sort of didn't talk about there is sort of what the status of principles in general, and I guess I would make a plug for thinking of this in a sort of relative a priori way rather than an absolute a priori way, somewhat targeting to what you think, the actual problematic that's in hand, what principles are going to be useful. Did I miss anyone? I think that was everybody. Is anyone sitting here feeling left out? Okay, I thought I had a list and I counted 10. Just a sort of final kind of thought there. When I talk about the value for philosophy, what's sort of nice here, I think what's really nice and sort of exemplified in different ways by the different talks, is we're not sort of talking about a kind of philosophy of science where it's sort of a case study that's sort of sitting there as some fossil that we're sort of dissecting to do philosophy of science. This is really kind of engaged with what's going on in the field as well, and it's the way I've been the way the question's posed sort of assumes a distinction between philosophy and physics that I don't really kind of fully believe in, or I think it's not a sharp distinction, and it's really nice to see so much work just like right at that border where both things are in play. So that's my thought about my sort of overall thought. Maybe I'll just say my thanks and then you should probably say thanks to the sort of some specific people as well. But can I actually say the thanks?
Yeah, you can say thanks.
My asking to say the thanks wasn't the thanks. And I know that's a thing that kind of happens, where you ask to say thanks, but So anyway, I thanked sort of everybody here for your participation. I did want to thank Chris sort of especially, and I would thank Kate as well if she were here. I mean, well, you said a nice thing for me, but you did all the, the groundwork organizing here, and sort of more than that, dealt very calmly with my kind of paranoid sort of freaking out emails about how things were going. So I really want to say thanks for being so kind of calm and generous with all that.
Well, the reason why you freaked out because you were doing most of the work.
And let me add my thanks to the crew who's been helping, Farshid, Pascal, Matteo, Todd, and Yishin, who've been setting things up, running the cameras, and doing everything. Kate, who isn't here, but who's the staff person at the Rotman Institute, did all of the work beforehand to help make sure things went smoothly. So thanks to all of them.
Some of the UIC people were helping me out as well, and Saakshi in particular to help with sorting out the website.